Okay. Hey everyone. Thank you for coming to our presentation. Um, we're going to be talking about the iterations and mechanisms. My name is Rishon. I'm an FRC 971 alumni. I was the CAD lead on our team last year, and I spent 4 years on the team.
And and my name is Anirudh. I'm a rising senior. I was this year's scouting lead. I've been on the team for 3 years, and this upcoming year will be my fourth.
All right. Our goals for this presentation. Our goal is to give insight into how we design mechanisms. We're going to be focusing on three main mechanisms that our team has built from the past couple of years that have had varying degrees and types of iteration. We'll also be talking about the prototyping process that our team utilizes. Hopefully, you'll walk away with an understanding of how we approach the design of mechanisms that have different amounts of risk and cost associated with their prototyping.
So this is the prototyping process. The first step is understanding the strategy of what your team is hoping to do at the game. This is what the robot will hope to do in a given match, and this is the first step and should always be done before prototyping. The next step is isolating mechanisms. This is simply separating different mechanisms that do different things on the robot from each other. For example, you would separate an intake from a drivetrain or the shooter from a serializer, as they do different things. After that, you come up with ideas for different mechanisms that can accomplish what your strategy outlines. So looping back to the first step, if you have more than one idea you want to pursue for a specific mechanism, you can prototype them in parallel and decide which one will go into the robot as you collect data. And then after that, you just gain understanding of what you need to learn from a prototype for a mechanism and what variables should be isolated. And then this simply means that you need to come up with some ideas of what you want to learn when you make your prototype and what you hope your prototype will help you accomplish. After that, you obviously make your prototype with your isolated variables in mind and you run it and record data. After that, if you are satisfied, you can move on into the CAD section. If not, you can repeat your prototyping process and change those isolated variables we were just talking about. And you can keep on doing this up until you need to start doing CAD or you feel like your prototype has accomplished its previous set goal. After that, if your prototype accomplishes your set goals, you can move on to doing CAD and translate details from your prototype that made it successful into CAD.
All right, the first mechanism we're talking about is the 2019 suction intake. And just as a quick refresher, although most of you probably remember, the 2019 season had two game pieces, the hatch panels and the cargo, which had to be placed in both the rocket and the cargo ship. So as a reminder of what our suction intake looked like, you can see how we had two different suction cups, one larger suction cup and one smaller suction cup. The larger suction cup was only used to grab onto the cargo, which is like these giant rubber balls, and the tiny suction cup was used along with the larger suction cup to grab onto cargo. The two were arranged in a Biden shape and were attached to telescoping tubes that were mounted onto a wrist that was on the carriage of our elevator. And basically, that wrist could turn 360 degrees and we had a two-stage elevator, so that meant that we could score and pick up balls in a variety of positions and heights. So yeah, that's a little bit of background of our suction intake. And basically, we're going to be going over the goals that we had when we were entering the prototyping process for this intake. So one of our first goals was to be able to pick up both game objects with the same intake. And another one of our really early on goals was to pick up balls straight out of the human player station. On top of that, we also wanted our robot to be able to quick turn onto the ball if it missed the first time. So basically, if we missed in taking the ball, we'd be able to turn our robot into the ball, and the suction cup would like kind of fold onto the ball and grab onto it like that. This was one goal that ended up being not as important as we thought as we progressed along the season, and we did end up changing our prototype because of that. And then a goal that we developed really late on into the season, once we were almost done with the suction cups, was being able to minimize the time it would take to replace the suction cups in the heat of the competition. So we'll talk more about how all of these goals influenced our decision making and the prototyping process in the next slide. So as we began experimenting with suction cups and got a better idea of the direction that we wanted to go, we were able to isolate the aspects of the suction intake that required more focus in the prototyping process. So for example, things like what kinds of materials would hold the ball better, the size of our suction cups, the arrangement of the cups, and some variables that came as we went even deeper into the prototype were like things like the depth of the cup, the types of foam we were using, how that foam was being attached onto the suction cups, things like that. And then so these were just variables within the cups themselves. There were also aspects of the intake outside of the cups that need to be tested, things that were a part of the suction system as a whole. So things like fittings that were being put into the suction cup, the vacuum pump, solenoids, and the size of the tubing that was being run between all of these things. So the last two slides kind of reference the first four steps of the prototyping process. And in order to demonstrate the sheer number and types of iterations, we're just kind of going to go in a somewhat chronological order of how we prototype the suction cup from like day one to the end. And we just think that's the best way to demonstrate the prototyping process that we use for this subsystem. So on day one of our mentors had 3 PIAB suction cups that we used for initial testing. You can see these right here. This is one of them. And after initially testing them, we realized that those by themselves didn't work on both game pieces. So afterwards, we took foam and put them on top of those suction cups. And after testing that, that actually did end up working on both the ball and the disc. So afterwards, we tested even bigger suction cups because, bigger cups equals bigger force. And although they showed promise, they didn't have much depth, and as a result, couldn't hold onto the ball very well. So in an effort to add depth to the suction cups, we turned to 3D printed lips. So this is one of our earlier designs for that. Basically, you can see a bunch of different versions, but the 3D printed lips were just like 3D printed things that we put on top of the suction cups, and they added more depth and area to them. So yeah, we spent a lot of time experimenting with different depths, and we learned that although more depth is good, the cups needed to optimize to work even better. So after messing around even more, the best configuration were ones that were deepest in the center and shallower along the edges. So yeah, you can see all the prototypes that we were working on during this time. And one of the other things that we were using during the prototyping phase was an old robot called Butterknife. And basically this was just the drive base of our 2014 Thor robot. And we mounted a lot of prototypes to this robot, but we mounted the suction cups on top of it. And basically being able to drive around with the suction cups gave us an idea of how they would perform in a real game. We also built a human player station really early on in the season, so we were able to drive up to it and see how the suction cups would be able to grab cargo directly out of it, and also how we were able to see how quick turning would affect the suction cups when we were trying to grab stuff out of the human player station. So it really gives valuable info as to whether or not the suction cups would meet some of the goals that we had set for them. So going back to the actual suction cups, one thing that we tried really early on were rollers that went around the lip of them. And this started off as a 3D printed ring that you can see right here with little slots for dowel pins to press into. And on top of these dowel pins were these like nylon rollers that could freely spin. So basically this design, as you can see like an early version right here, really helped us when we were quick turning into the balls that were in the human player station, because without them, the suction cup would kind of flex out of the way. But with them, it was able to really roll onto it and suck onto the ball. And it really helped us meet one of the original goals that we set, like I said before. Another variable that we messed around with were the bellows. Basically, those are like the green squishy areas of the suction cups. And basically, we just wanted to see whether those bellows were actually necessary for the suction cups to perform. So we tested that by just like squishing them down and then taping them together, and testing the suction cups as normal besides that. And we learned pretty quickly that the bellows were necessary for the suction cups. But it's just an example of how testing individual variables is really important because it gives you valuable information. So yeah, basically most of our prototyping with the suction cups was just messing around with different 3D printed lips to see which shapes worked best. And once we got to a final prototype that we're really happy with, we had set another goal for ourselves, which is to think about replacing these cups at competition. So for the majority of our prototyping, we were attaching the foam on our suction cups to the 3D printed lips via glue. And the problem with this was the turnaround time for replacing cups. Basically, glue made it really difficult to Well, okay, like if we were to start at the beginning, if a suction cup went through wear and tear at a competition, the way we pack spares is we would bring whole like extra suction cups with us, but we couldn't bring very many of those just because of a lack of material. So a way to reuse cups is just by replacing the foam on them, and then putting the cup back on. However, as you can see, glue makes it really difficult to pull the foam off of the cup, and glue basically made a cup unusable. So we ended up switching to attaching the foam by pinching it by taking a 3D printed ring. You can see that in this picture right here. And this 3D printed ring had holes for screws, and those screws would go through the foam and into the 3D printed lip behind it, and that's how we secured the foam in a way that made the foam really easy to replace. Um, so this top prototype right here, you can see that it still had the rollers, and it was one of our final prototypes, but it was also before we got rid of the rollers, and it was around this time that we realized that like after having a robot that could actually drive and interact with the human player station, we realized that quick turning into the human player station and grabbing onto the ball that way wasn't actually that useful because we could do the same thing just by backing up the robot and going back inside. So we ended up switching our prototypes by getting rid of the rollers and going to this right here, which is what our final suction cup ended up looking like. And another thing that we messed around with was the arrangement of the suction cups. So like one of our really early physical prototypes was three mini suction discs that were oriented in a triangle. I don't have a picture of it, but some of the other ideas that we're messing around with were a trident with one big cup and two small cups, and then a donut cup with a big cup and a small cup inside of it, and then a bident with one big cup and one small cup. And the picture on the right over here, that's early prototype of the bident. So yeah, as you know, our final design ended up using the bident. So the 2019 suction intake was one of the most iterated mechanisms 971 has ever built. One of the reasons we had this many prototypes was because the physical iteration was low risk and relatively low cost. In addition, there wasn't much of a precedent for suction cups in the FRC community, so most of the subsystem was made on the fly, as you can see by the extensive prototyping that we did. However, not all subsystems are as easy to prototype, and the physical prototyping isn't the only way to test mechanisms. The other two mechanisms we're going to be talking about utilize different methods of iteration to achieve a working final product.
Okay. Like Rishon said, the large number of physical iteration that went to prototyping the suction cup intake was possible because of the low risk and relative low cost of continued iteration. It was significantly harder to physically prototype the next mechanism we will be talking about, and as a result, we iterated upon that mechanism using CAD, extensive math, and stress analysis methods. Moving to the next slide, you can see that our next mechanism is 2018 ARM. For those of you who need a refresher, this game essentially had two switches and one scale, and there was one big scale, you can see in the right side of the slide, bottom right, where you would place those yellow objects, cubes, onto them, and obviously the scale would tip to the side along with the switches, which would also tip to the side with the most weight or most cubes, and whichever alliance placed the most cubes, the scales and switches would tip in their favor, and they would get passive points, and that was essentially how you would win the game. Our strategy for this game was specifically to be able to have a robot that could reach inside the scale and place cubes in a much more controlled fashion, because we believed that would help us be able to make a large amount of stacks of cubes. And this would help us in competition, as we believed fighting for the scale was going to be extremely important. This is why for our placement mechanism of cubes, we decided to use an arm, or a double jointed arm specifically, because we could reach inside the scale using a double jointed arm. You can see a picture in the top right over there. The double jointed arm has two bits, or two arms essentially. Both of them are carbon fiber pieces, and the bottom arm is attached to a sprocket at the very bottom in the gearbox. And so there's a sprocket, and you turn that bottom sprocket and it turns the bottom bit. And we have string that turns a pulley at the very top of the arm, which turns the second bit of the double jointed arm. And it gets the name double jointed because there's two joints on it. So moving on to the next slide, you can also see other parts of the arm. You can see the gearbox at the top right. It was a very big gearbox, and you can see the sprocket along with the chain modeled in, which moved the arm. Also in this gearbox, we actually had our gearbox for our hanger also. So that's why it's very big. and looks kind of complicated, but it's actually two gearboxes in one. Also at the bottom or middle bottom, you can see our grabbing mechanism. What we did is we took a piston and we stuck it inside the carbon fiber tube. So what the piston would do is the piston would retract and it would pull on some string, which would pull the two claw bits together, clamping on the cube. And we believed that would be the best method for grabbing the cube. And so that's what we did. So and you can also see a picture of the gearbox actually assembled at the bottom left. So physical prototyping and iterating on the double jointed arm would have been high cost and effort because the entire thing was pretty big and made out of carbon fiber. We made a smaller prototype as proof of concept just for like a double jointed arm like working, but making the arm durable and controllable required much more than that. So obviously we couldn't make a physical prototype for that. So as a result, we relied on doing heavy amounts of math, stress analysis, and Crayola CAD to ensure that the arm would work the first time we made it instead of prototyping it. This math included trying to balance out all of the forces in the arm and balance out the torque of moving the arm. So we used a very big sprocket at the bottom to move the arm and a big pulley at the top to move the other joint of the arm. We also had to calculate the PSI of the epoxy to ensure the seal didn't break under the stress of the arm and calculate the stress. And we had to calculate the general forces and stress of the arm using finite element analysis or FEA. You can see at the bottom right where it's like a heat graph that shows like different parts of the mechanism where there's more or less stress. And so we did that for the arm to make sure different parts of the arm didn't go through too much stress that it would damage it or break it. The double jointed arm, so that's how we made the arm. So moving on to the next slide, you can see the arm in action. You can see at the bottom right how the arm is reaching inside the scale like we hoped it would. And you can also see how our arm, how our arm also had our climber, had like a climbing bit attached to it in the top right, and it's carrying up another robot. And you can just see the arm just placing a cube on the other picture. The double jointed arm is similar to the suction intake as it was a subsystem that was unproven in FRC. No one else had built a double joint arm before us. The main difference between these two is our execution of the concept. One, the suction cup, while it was very small and low risk to continue iterating, so we were able to just continue kind of like brute forcing the prototype while the arm was very hard to make a physical prototype. It was high effort and obviously expensive. So we were forced to kind of prototype and iterate on it virtually using methods like Crayola CAD and industry practices to build it correctly the first time it was made. So both the suction cup and the double jointed arm were mechanisms with no precedent in FRC. As a result, they relied on heavy iteration in order to make them functional. The last mechanism we will be talking about is one that has been used many times in FRC and required little physical or mathematical iteration to get right. Instead, we focused on choosing a style that suited our robot's goals. So, moving on.
Okay, so our final mechanism is the 2019 elevator. The elevator consisted of hollow rectangular carbon fiber tubes that were part of its two stages. And the carriage on the elevator carried a wrist that could rotate 360 degrees, like I mentioned in the suction intake part of the presentation. And again, our suction intake was mounted to this wrist, so we were able to score in a variety of positions at a variety of heights.
Yeah, so this game had two big pieces. There was the cargo ship, which you can see in the bottom left, which is in the center of the field. And at the top right, you can see the rocket, which is on either side of your aligned side in the game, which had 3 levels you can score on. And so this game, in order to get the additional RP, you had to climb and you had to, or in order to get an additional RP, you could either climb or you could fill up one rocket with 6 hatch panels and 6 balls. You could do both and win the match and get 4 RP. So this year we decided we want to be able to do all 3 levels of the rocket. So we decided we would need some type of elevator to do that. Our strategy, we believe this game would be a heavy amount of cycling. So we wanted to have a robot that could cycle very quickly. And so what played into that was having a very fast and small robot so we could travel quickly, and having a robot that never had to turn when it was going to score. So the robot would be able to intake on one side and score on the other. So essentially it had to be able to score on either side of itself. So moving on to the next slide, you can see the different types of elevators we were considering when we were making our robot. So when deciding how to move forward with this mechanism, we decided not to make a physical prototype as it was unnecessary due to an elevator being a proven concept. In the early stages of the season, we had 3 ideas for elevators. At the bottom left, you can see one idea was a differential elevator. This isn't actually our Crayola CAD for an elevator. This is 3847's, but this is just a picture of a differential elevator. And then in the center, you can see the Crayola CAD for just a simple continuous sideways elevator, which is eventually what we used. And at the bottom right, you can see a tubular elevator that 148 had in 2018. When deciding to move forward or iterate on this, when deciding to iterate on the mechanism, we started doing Crayola CAD. We eventually learned that mounting a tubular elevator would be very hard as the tubes are obviously circular, and it doesn't really carry that much of an advantage packaging wise over just an elevator with rectangular tubes. So we ruled that idea out through using Crayola CAD. And then for the differential elevator, we eventually learned that what differential elevator is a little easier to string than a sideways elevator, but you run into issues where since it's not a sideways elevator, you need the game pieces to swing through the elevator. So with big game pieces or wide game pieces like the ball and the hatch, we couldn't have a small and fast robot. And also a differential elevator is just more complex. So we decided to go with the simplest idea, which we believed would work, which was our sideways elevator, which was a continuous elevator. So you can see pictures of it on the next slide. So you can see it scoring at the bottom right. This is one example of how goals of a mechanism can drive early decision making, as we wanted a small and fast robot. So we wanted a very simple and small elevator. And so this obviously ruled out a differential elevator as it was very big. And also how Crayola CAD can really help you out when prototyping, as we learned a tubular elevator was very hard to mount by doing Crayola CAD. Essentially what we did for this mechanism is we took a proven FRC mechanism archetype, which was like the elevator, and we analyzed like different specific cases of it when it has been used, specifically tubular elevators, differential elevators, and just a simple continuous elevator. And we evaluated each idea based on our robot, and we chose one and tailored it for our use that year.
So to sum it up, when iterating on a mechanism, the most important thing to test is its ability to accomplish the goals that you've set for your robot. There are different ways of doing this, and the 3 mechanisms that we've mentioned are examples of that. They've undergone varying degrees and levels of iteration. So hopefully we were able to give you insight into how our team designs different robots and mechanisms from the ground up. We'll take any questions now.
Oh, we have some questions in the chat.
Oh, in the chat, okay. Okay, so the first question, how long did the suction cup prototypes take to make? And what advice do you have to decrease iteration time? So the suction cups actually progressed pretty quickly. I think we started testing the initial cups on like day 1, and I would say that the main time waster, I guess, was like ordering stuff, because we had to order things very quickly and make sure that we had everything we needed to make progress in like the following meeting. So like buying bigger cups, buying different foam, buying different solenoids, buying different vacuum pumps. That really is something that we had to account for when we were prototyping. And another thing that we also take into account was 3D printing. So like a lot of the lips that we had were complex 3D prints that took like a significant amount of time to make. So I guess there's no really easy way to answer your question. Like every iteration took like a different amount of time, but we tried to make as much progress between meetings as we could. So like we would order things between meetings, we would print things between meetings. So like we would make significant progress between when we would next meet. So yeah.
Like generally some advice be like just kind of coming up with some plan. Like if it's going to be some mechanism you plan on rapidly iterating on in a short amount of time, you would have to like you kind of just have to come up with some plan of we'll order something by this, and we want this question answered regarding this mechanism. So we're going to make this. So then you obviously, your biggest time blocks will be ordering and getting something to come and 3D printing. So just generally managing those time blocks along with what you hope to answer by a given amount of time. It's the best way to do it. So coming up with some plan. Were you working on other intakes in parallel with the suction intake? We tried out some other intakes using rollers early on. We also tried using pistons, like piston hooks for the hatch. But early on, we kind of ruled those out and just decided to use suction cups. I believe we decided week 2 or 3. It works, you know, to guarantee. What's a differential elevator? Here, can you go back to the differential elevator slide?
Yeah, 1 second. There we go.
So a differential elevator, it's essentially the same as another type of elevator, but your intake is able to kind of flip through the inside of the elevator. So another example, while not like a perfect differential elevator, would be 254 in 2018, where their intake could essentially, I believe their intake would go on either side. Oh, actually, no, that doesn't count because their intake came out the top. But you can see it in this picture where their intake essentially swings like through their elevator for the bottom left picture of 3847. Can you explain how the elevator, can you explain how it works, the elevator system, to guarantee the linear movement? A differential elevator moves the same as a continuous elevator. And a continuous elevator simply has string that you attach to the top stage and the bottom of the top stage. And what it does is the string essentially pulls up, you retract the string and it pulls up on the stages, and the stages come out linearly, if I'm understanding your question correctly.
All right, do you want to answer the next one?
So a differential elevator is an elevator with a pass-through. Yeah, that's essentially what it is. You can move through the middle. You could also, depends on who you're talking to, but you could also say, or I'm sorry, I forgot what my point was. Yes, a differential elevator is one with a pass-through where you can move through the middle or in between the two supports. How much do you want to talk about this one, Rishon?
Yeah, sure. So I believe that the 2018 ARM was a bit of a special case in that like we said before, it was something that really couldn't be physically prototyped, so we had to be really careful in its assembly and design. So like doing finite element analysis on it, it was really important, especially since it was made out of carbon fiber. I am not entirely sure about this, but I believe that we might have done stress analysis on the 2019 elevator as well, because that was also made out of carbon fiber, but it's not something that we do very often. Oh, sorry, I didn't read the question, sorry. The question was, how much do you rely on finite element analysis and other stress analysis rather than physical prototyping? So yeah, that's what I just answered.
Yeah, I was, yeah, it's all.
So the next question is, how are you planning to teach prototyping to rookies this year, given quarantine, and how did you do it in past years? Anirudh, do you want to answer that one?
Yeah, sure. So generally, we find it's best to teach something like prototyping by like doing. We have some introductory slideshows will or presentations we'll give to new members about about like the timeline of a season, and like we'll start prototyping here and stuff like that. And we also do talk about like the value and I guess the lifetime of a mechanism on our team. But we think the best way to do it is to kind of just have new members just like essentially we have groups working on different mechanisms at the beginning of the season and kind of assigning a new member to a mechanism they feel passionate about is the best way to get them to learn. As for in quarantine, sadly we can't really do that, so what we've been doing is just kind of like giving presentations and offering like previous examples of like this is what a prototype for this mechanism looked like in like that season. um, the next question is, what's the difference between a differential elevator and a telescoping arm? Um, well, a telescoping arm isn't really an elevator, as an elevator usually relies on string or chain to be driven. You can also drive in other ways. And they're not like a differential. What makes a differential elevator is that it has a pass through in the middle. And a telescoping arm is just there's like no pass through to be like seen. I'm sorry if I'm not doing a good job. They're just like kind of not really like one's an elevator and one is a telescoping arm, and a telescoping arm is similar to an elevator, but they're not quite the same. Anyways, moving on.
So next question was, what have you been your personal favorite mechanisms to iterate on? Um, I would say that, do you want to go first? I need to think about this one, actually.
My favorite mechanism to iterate on. I would like to say the 2020 R shooter, I did a big part of early prototyping for that, and I thought it was just very fun because you get to like make something that shoots balls really fast. That's like a very personal thing that like I like. As for like other mechanisms, um, I would say also the 20. I would say it's probably the 2020 shooter. I obviously can't like reveal what we did, but like iterating on a shooter is just like kind of fun because you get to like just make something that shoots stuff really fast. Sean?
Yeah, I think I'm gonna agree with you on that one because we did work on the same prototype that year. So yeah, iterating on the shooter was pretty fun. Um, I would also say that I did work a little bit on suction cup prototyping at the beginning of the 2019 season. I actually worked on the triangle arrangement with the discs, and although it didn't work very well, it was still pretty fun to work on something like that. So yeah. Yeah. The next question is, does the process stay roughly the same for you in the off season when building robots for events like Madtown Throwdown, or are there major differences? Um, so in the past, what we've done is once the season has ended, over the summer we'll make a third robot with that is just built entirely by students, and that's the robot that we'll take to Mad Down Throwdown. So it's definitely a different process because uh, we get so much more time to make the robot, but the meetings are also shorter. There's less time pressure like in the season. So but the process of like prototyping and taking it to CAD and then fleshing out the design, then manufacturing and assembling it, that stays the same. It's just like it's spread out over a longer period of time, and it's really only students making it. So yeah.
The other question, that's a picture of a telescoping arm. Um, oh, I see. So the question is, uh, the Crayola cat in the picture is a telescoping arm, which is why I'm confused. Um, yeah, we were looking at this picture as it's not a 971 picture, but I believe the arm is supposed to move 180 degrees this way, and the reason it's up like that is because it's like that's just a part of like its movement. But if you know another like story to that picture, it's a telescoping arm, then we apologize. But we interpret it as a differential elevator with a pass through, and it's just like not that tall. Anyways, Sean,
Okay. I guess so. The next question was, can we get any insight into your 2020 robot? And that is the answer to that is no, because the next season is going to be iterating on it's going to be the same game, right? So we can't really talk about a robot.
see,
Yeah.
Rishon is actually wrong. I can give you one insight. We have this cool system that relies on actual suction cups as intake. So we have like 5 of them on a roller, and you just spin it really fast and run the vacuum, and you can just run around and you pick up like all the balls on the field, and your robot can just kind of run around on the field while the refs try and steal the balls. But since they're suction cups, you just can't steal them.
Yeah, that's
Anyways,
my bad. Anirudh is right on this one. That's exactly what a robot is. Yeah.
yeah, that's why we haven't released it yet. It just doesn't really work. Um, moving on to the next question. When making multiple prototypes, do you assign people to specific prototypes or have everyone work on all of them? Generally speaking, when we start the season, a senior member will have some senior member take lead on a prototype. And if you're newer to the team and don't feel like particularly anchored to any prototype, you can kind of just do whichever prototype you want. Like if you want to work on the shooter one day, you can. If you don't, you can work on like the intake or something else. But generally, we have one senior member leading the prototyping of one mechanism or one specific prototype for that mechanism. Sean, would you like to do the next question?
Sure. Yeah. The next question is, how would you recommend teams with small budgets pursue more prototyping? Um. Huh. Uh. I guess being able to making sure that you're developing mechanisms that are within your means to prototype. Like not everyone has 3D printers like we do, and not everyone has like the manufacturing capabilities that we do. So making things out of wood is especially like is really good for cheap prototyping. We do that too, actually. We make things out of wood all the time, and just making sure that you prototype and develop mechanisms that are within your means to do. Um,
Yeah.
yeah, wood is really good.
Yeah. Adding to what Rashawn said, you don't always need to just have like the coolest idea. One thing that's always very helpful is there's a wealth of resources about different FRC mechanisms, and you can just kind of take what another team has done in a previous year and just kind of appropriate it for this year. And that's what we do with the 2019 elevator. And in a lot of situations, you don't need to actually physically prototype, which is where a lot of the cost comes from. The next question. Any advice for a team with a CNC router during the prototyping phase? One thing our team has found is really helpful is making prototypes out of wood, because you can do that very, very quickly on a CNC router. And just generally, as like an FRC team, you want to use all resources you can use as possible. So like you can make some pretty high effort prototypes, which can be very close to your robot and can answer a lot of questions. And you can very quickly prototype using wood on CNC. Do you have anything to add, Rashawn?
Uh, no, I think you got it. Yeah, I mean, a lot of our prototyping, we CAD a lot of our prototypes as well, and depending um on the prototype, obviously, but like things like shooters, we would CAD prototypes of those, cut them out of wood, and then assemble them, and then and like make places to mount motors, like mounting encoders and things like that. So you can do a lot by CADing wood and using a CNC machine to cut it. So yeah. Um, the next question is, do the suction cups also compress the balls? They do not. Uh, they kind of just latch onto the surface and don't compress it, I believe. I could be wrong on that. But yeah.
Also using a pneumatopult.
I
The
think
question is,
I think that's a joke.
I mean, a pneumatopult, we could be using that. It's probably the second shooter on the robot.
Yeah, we've actually had 5 shooters, one
Yeah,
for each ball.
it's gives more variation for the crowd.
Yeah.
Also, just look at the robot, get really confused. Next question, is your robot also attached to the carpet while shooting with suction? Um, that's a great question. Sadly, we we considered the idea when we were just shooting balls so quickly it would move the robot a lot, and we were just thinking about it, but we just lowered the RPM on our shooters and we never had the issue of our robot moving enough. So sadly, we do not attach the carpet while shooting with suction. Yeah. Would you like to talk about the next question, Rishon?
Yeah, yeah. So, how do you guys deal with safety while prototyping, slash tips on prototyping safely? So on 971, we really put an emphasis on safety, just any time. You're not allowed to be in the lab without safety glasses. We have supervisors that have to be in the lab at all times. Anytime there's someone is in the lab, regardless of whether or not they're using tools, you need to let the supervisors know if you're using any high-power machinery like the lathe or the router, and if you plan on cutting things outside. You have to let them know. Like really, safety is super important for us. We have sheets that outline how to use power tools properly when we're in the lab. Um, yeah, and like every member has to go through 2 levels of tool training in order to be able to use tools on their own. Every member has to take a safety test. Really, like safety isn't only limited to like prototyping, like the question said. We take safety super seriously for every part, every single day that we're in the lab. So yeah. Favorite prototype. Okay, so next question was favorite prototype that got shelved. Um, I want to say the 2017 serializer prototype that we made out of wood was pretty cool. It had like I don't remember exactly how it worked, but it had like these. It had to hang off of the ceiling with like a bunch of wires, and it would like uh, it would climb up pretty quickly off of that. I know it sounds super vague. I'm trying to find a way to describe it, but I remember that prototype was pretty cool. Um, Anu, do you want to answer the same one?
My favorite prototype that got shelved. Um, we shelved a pretty cool serializer prototype this year. We can't really
Oh
talk
yeah,
about
this
that.
year, yeah.
Um, I don't know. We didn't prototype it, but I thought it would have been interesting if we had tubes for an elevator last year in 2019. It wouldn't have made that much difference, but it looks much cooler. Next question is, how much time do you spend designing, prototyping, and testing? Generally, we try and spend, well, it depends on the mechanism and how much refinement we want on it. For example, last year in 2019, I believe we didn't really stop prototyping the suction cup for most of the season, but every other mechanism stopped at around week 2-ish, and we just started doing CAD, and I believe we finished CAD around week 4, and that's when we started fabrication. This year, however, we decided we wanted to have like a very good shooter, so we spent extra time on simply prototyping the shooter and just took the downside of that. Maybe at our first competition we put a shooter where not we put like an older prototype of the shooter onto the robot, and we don't perform as well at the competition, but we have a much more tuned up shooter for our later competitions. So it really depends on the mechanism and how much like how refined we really want it to be. As with like our shooter this year and with our suction cups last year, we really wanted them refined. But with other mechanisms, we just kind of cut it off at like week 2 or 3.
Yeah, so like Anirudh said, we try to walk into the season with potential deadlines for ourselves in terms of each step of the process, and being able to finish prototyping by week 2 is like it's a pretty ambitious goal when it comes to certain prototypes, but it is a goal, and sometimes we choose to refine the prototype more, and sometimes we choose to move on to the CAD phase, but that's very rare. We like really try to make sure that the prototype does what it's supposed to before we move on to the CAD phase. So it's very different depending on the mechanism, but we do try to set a goal for ourselves to finish early on in this season, because CAD does take a while. So
next question is, when do you decide to use finite element analysis? I assume this is asking kind of about like a general rule. Generally with the arm, it's kind of hard to tell where the forces are gonna, or where the stress in the system is gonna be, as both of them are actually, both parts of the arms are moving parts. So you would use that to just kind of calculate stress. I believe anytime, if you're gonna use carbon fiber, you probably should, because carbon fiber is a brittle material, and you can get in some trouble if you just kind of break some carbon fiber because you didn't really check out the forces. Generally speaking, you should probably draw at very least a free body diagram for every mechanism you make to just understand forces and try and just balance them out, so you're not putting too much stress on different parts of the robot. But if you want to go like, also just like, you should, if you're gonna do something where the free body diagram is just kind of really complicated, it's probably good to do something like that. There's not really a general rule for it, other than you should have an understanding of the forces that are happening in your system, and stress analysis can really help you with that. If you like, if a free body diagram gets too complicated, or you just like don't understand it. Sean?
yeah, so the next question, okay, so there's a couple questions that kind of talk about the same things. There's like, when do you start CAD in the prototyping phase? How much time do you spend designing, prototyping, testing? And what's the rough prototyping schedule for when you're operating without bag day? I would say that to answer all of those questions, for this past season, we really tried to go into the season with the expectation that we would be following the guidelines of a season with a bag day, and then take the extra time to really take advantage of driving the robot around and making sure that our driver gets really good with that robot. We weren't able to stick to that schedule, unfortunately, but the goal is to take 1 or 2 weeks for prototyping, and then another 1 or 2 weeks for CAD, and then take like maybe 1 week for assembly, and then try and get as much drive practice as possible. That's the schedule that we try to work with. There's definitely like changes that get made to that schedule based on as time goes on, and based on like um, I guess like different factors of the season. But that is the general goal. We do have trouble sticking to that schedule though. So
Yeah.
oh, the next question is, what does your CAD timeline look like, and how do you manage a multi-person CAD team? So when we get to a point in the season where we know what subsystems we're CADing, we try to set deadlines for those subsystems so that we can hand it off to so we can check off the subsystem and hand all the parts off to manufacturing as soon as possible. And in terms of distributing CAD work, the CAD lead is supposed to maintain a kind of like an overhead view of all of the CAD tasks that need to get done, and then assign them to certain people. So some people get like subsystems that they work on throughout the entirety of that subsystem's CAD phase. And we also try to incorporate new members as much as we can so that they can learn as much as possible from the experienced CADers that are working. And yeah, mentors also play a huge role in the CAD phase. We try to work with mentors as much as possible on CADing things. Yeah.
Yeah. Good job. Someone asked to make the prototype of your shooter this year. Did you build the parts with the CNC? We did use wood for our prototype of our shooter, and so we used our CNC router to cut it.
Okay, I think we might end it here because we're not really getting any more questions. So yeah, thank you everyone for coming. This was our first Spartan series, so we apologize for any technical difficulties that we had. But yeah, thanks for showing up. Thanks for listening. Thanks for all of your questions. Yeah.
Yeah, thanks.